Okay, so let's work for the strong convergence, almost sure convergence. Okay, so let's work on almost sure convergence. So remember that to show that some sequence converges to some random variable almost surely, we had certain results, certain corollaries of Borel-Cantelli lemma. So recall that if we have, for every epsilon, if we look at, now I should write Sn over n minus a. So this was like the xn in the generic sense, and this is the x, which is the limit, okay? So now we have Sn over n versus a. So we look at the probability that the distance between the two is larger than epsilon, and add those probabilities from n1 to infinity. Okay? So if this is finite, then Sn over n would converge to a almost surely. So this was a corollary of Borel-Cantelli number 1, says this. Okay, so let's see if we can use it. So Sn over n minus a greater than epsilon. So if you look at expected values, these are just constants, right? But if you look at the variance, this is b over n. So if you can use Chebyshev's inequality to relate it with the variance, so which says variance of Sn over n divided by epsilon squared, since this is just the mean of Sn over n, right? So the distance between a random variable and its mean, the probability that it is greater than epsilon is less than variance of the random variable divided by epsilon squared. This is just squaring both sides and applying Markov's inequality. So this is b over n epsilon squared. And if you add those probabilities, unfortunately, it is not a convergent series, right? Unfortunately. We have 1 over n, sum of 1 over n's just diverges. So this test fails. This test fails. Under what condition? So if you had what, you would have a convergence series. So instead of 1 over n, if you had something else, you would have a convergence series. For instance, what? 1 over n squared, right? So if we had 1 over n squared instead of 1 over n, we would have a convergent series. Indeed, if you look at as k squared over k squared, so if you look at the subsequence, so instead of looking at indices 1, 2, 3, 4, 5, just look at 1, 4, 9, 16, etc. So this is less than, by the same logic, so k squared epsilon squared, k from 1 to infinity. This is b over epsilon squared, and 1 over k squares, I think the sum is pi squared over 6, but the value isn't important, so this is just finite. So indeed, we don't have almost sure, we couldn't get almost sure convergence for the full sequence, but we get as k squared over k squared goes to a almost surely. So we have almost sure convergence for a particular subsequence. So let's try to extend it to the full sequence. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. So right now we look at 1, 4, 9, 16, right? S1 over 1, S4 over 4, S9 over 9, S16 over 16. That sequence converges to A. How about the full sequence? So let omega 0 be the event of almost sure convergence for the subsequence. So we have that the probability of that is 1. So pick omega from omega 0. So we look at one particular realization. Okay? One particular realization. So the idea is to make the full sequence converge using the fact that it's one particular subsequence converges. Okay? So if we have an arbitrary index n, this is always in between two squared indices, right? We can always find some k squared and k plus 1 squared such that n is between the two, right? So if I look at Sn, which is just a bunch of terms, I would be able to say that sk squared is less than Sn, and this is less than sk plus 1 squared, if I were to accumulate positive values. If they are negative, I cannot say that, right? If I add negative values as I increase my index, this wouldn't be true. So let's add the further assumption. So assume further that xi's are all positive. We're going to relax it at the very end. For now, let's just assume it. So if we have positivity, we're just adding more positive numbers. So the sum can only increase. Can only increase. OK. So what are we interested in? Sn over n. Right? Let's divide everything by n. Okay. So if so I have a mismatch between my index here and my denominator. Okay. And unfortunately, I cannot write sk plus 1 squared divided by k plus 1 squared because n is smaller than k plus 1 squared. So 1 over n is only bigger than 1 over k plus 1 squared. I can only have this. I can only have this. But this is no big deal because we can always rewrite it as k plus 1 squared over k plus 1 squared times k plus 1 squared divided by k squared. Okay, as a product of two terms. And we know that this just goes to 1 because they have the same coefficients, right? K plus 1 squared over k squared just goes to 1. And this goes to A. Okay, for that omega. Okay, for that omega. I forgot to put omegas. Omegas. Everywhere. Okay. For that omega, this goes to A. Because we have convergence for that subsequence, right? If xn goes to x, then xn plus 1 also goes to x, right? So we have k plus 1, it's fine. We have to do the same thing over here. So let's see, sk squared over n is larger than sk squared over k plus 1 squared. Because n is smaller than k plus 1 squared, so 1 over n is bigger than 1 over k plus 1 squared. And this I can write as sk squared over k squared over k plus 1 squared. Just the same trick. And for omega, okay. Again, this goes to 1, this goes to A. So I have convergence to A on the left, convergence to A on the right. So by sandwich theorem again, so Sn omega over n goes to A for that omega in an almost sure set. So we're done. We're done. All we have to do is to remove the positivity assumption. So finally, let's remove positivity assumption. Well, what is Sn over n? It is x1 to xn over n. And each x1 is x1 plus minus x1 minus. So I can write it as indeed like sum over pluses minus sum over minuses. And since both are positive sequences and still IID, this converges to expected value of 1. This converges to expected value of the first term, right? Now I cannot write A, because A is what? A is just the mean of one of those IID random variables. Here, the IID random variables are those, so I have to write the expectations of them. Okay? And since these are integrable things, the limit is going to be just expected value of x1, which is A. Okay? And just a little detail, this happens almost surely, this happens almost surely. Then this means their difference converges to A almost surely. Because if you have convergence almost surely for two sequences, you can add them and still get almost sure convergence on the intersection of the two almost sure sets, right? Which is another almost sure set. Okay? So you have, for the pluses, positive parts, you have almost sure convergence. For the negative parts, you have almost sure convergence. Just intersect the two sets on which you have almost sure convergence. Then the intersection is another almost sure set on which you have convergence for both parts, right? So the intersection of two almost sure events is another almost sure event. And this finishes the proof of law of large numbers. Strong and weak. Well, I just like to discuss with you some very well-known examples from statistics. You know, there is always this X bar thing appearing in statistics, right? It is just arithmetic average, just this, right? And this converges to the true mean. So this is simply law of large numbers, okay? So, and a further special case of this happens in the Bernoulli process case. So let's say you have a Bernoulli process. With success probability P. So those are IID Bernoullis with success probability P. Then what do you have? Well, Sn is just sum of xi's, right? So Sn over n converges to expected value of x1, which is just P. So what is Sn? It is the number of heads in the first n trials. And what is Sn over n? It is the fraction of heads in the first n trials. Okay? Almost surely. Almost surely. So just to write it more carefully, what are we saying? We're saying that the limit of Sn over n as n goes to infinity is equal to p with probability 1. So this is a justification of the so-called frequentist approach. You know, if you want to calculate or estimate the probability that you get heads, all you can do is to just run the experiment or just have so many trials, like 30, 40, 50, and then look at the fraction of time you get heads. This is an estimator of the true probability of getting heads, right? So this fraction is just Sn over n, and you use it as an estimator of p for two reasons. One reason is that its expectation is p. Another reason is that it converges to p as the sample size, which is n, gets larger and larger. Right? And there is a variance version of that. Let me state it for the general case. So xi just IID. So this 1 over n xi is the sample mean. Let me write it here. And this converges to just expected value of one of them, which is A, right? This is law of large numbers. But you also have, for instance, if you square them, so x1 squared, x2 squared, x3 squared, they are also IID random variables, right? If you have IID random variables, apply any function to them, you get a new sequence of IID random variables. They are still independent. They still have the same distribution because you just apply the same function. Okay? So x1 squared, x2 squared are also IID. So by law of large numbers, this converges to expected value of x1 squared. And in fact, there is the so-called sample variance. Okay, sample variance. So if you just write down this expression and use these two facts, you can just check that this converges to the true variance. So these are all almost surely. Right? You need then n minus 1. If you have n, you get not the true variance, but so you don't get the true variance. Okay. In fact, you can apply any function to xi's. Let's say f bounded or continuous, whatever. Just make sure that these have finite mean and variance. So this converges to expected value of f of x1. Let's say nu is the common distribution. You can calculate it as an integral like this, right, on R. Again, almost surely. Okay. Any questions? So sometimes when you use those things as estimators, they're called strongly consistent because they converge to the true parameter that they're trying to estimate with probability 1. Okay? So there is this notion of consistency of estimators in statistics. So consistency means as you increase n, you're approaching to the true thing, to the parameter that you're trying to estimate. And indeed, you have strong consistency because you have strong convergence, strong law of large numbers, almost sure convergence. Okay. Okay, so the last notion of convergence we're going to discuss is convergence in distribution. Okay, so for this, so this is about, let's say you have x1, x2, etc., and an x. Okay, so these are the random variables, and these are their distributions. Nu1, nu2, and this has distribution nu. So this is about, convergence in distribution is about the convergence of the sequence of distributions. Okay? So what do we mean by convergence of a sequence of distributions? Convergence of a sequence of probability measures. Okay? We have to specify that. So this is the notion of convergence for distributions is called weak convergence. So I'd like to give you a definition first. So let nu n be a sequence of probability measures. Not necessarily distributions of some random variables, but I just stated in a more abstract way on the real line. Let nu be another probability measure. Again on the real line. We say nu n converges to nu weakly if nu n f converges to nu f, okay, for every bounded continuous function f. So what do I mean by nu n f? It is just the integral of f with respect to nu n. This is just the integral of f with respect to nu dx. So distributions or probability measures are kind of abstract objects. So to be able to talk about their convergence, what you do is to integrate some test function f with respect to them and let those numbers converge. Okay? So once you take an integral of a function with respect to those measures that you have on hand, you get real numbers. So now you can talk about the convergence of those real numbers. Just to give you an idea, let me give you an example. Okay, so we're going to look at the uniform measure on the set so 0, 1 over n, 2 over n, to 1. In other words, nu n is nothing but sum of Dirac measures. We should have just n points. So 1, 2, 3, n over n. So we have n points, okay? So 1 over n, k from 1 to n, of the Dirac measures at k over n, okay? So 1 over n, 2 over n, 3 over n, etc. Just assign equal mass, 1 over n, 1 over n, 1 over n, 1 over n, equal probabilities to all those points. So now what is nu n of f? What is nu n of f? This is the Dirac measure with respect to f. What is the integral of a function with respect to the Dirac measure? Do you remember? What is the integral of a function with respect to the Dirac measure? Just the value of the function at that point, at the point of the Dirac measure, right? So this is just 1 over n, f of k over n. Now what is that? This is a Riemann sum. Riemann sum, if you take your grid as 1 over n, 2 over n, 3 over n, etc., you just look at the function at each point, right? So 1 over n, 2 over n, 1. You just evaluate your function, f1 over n, and this is, the length is 1 over n. You evaluate your function at 2 over n, then this is your length, 1 over n. So you just calculate the areas of those rectangles. So that's the Riemann sum. So if you let n go to infinity, this converges to the Riemann integral, 0 to 1, f of x dx. This means it is the integral of f with respect to which measure? If you have dx, Lebesgue measure. So this is just Lebesgue f. What does this tell us? What does this tell us? This tells us that those discrete uniform measures converge to the continuous uniform measure, which is Lebesgue. Okay? So maybe in your mind you can see those discrete uniforms and the continuous uniform, which is Lebesgue, as separate things because they are discrete. This is continuous. But indeed, there is a way to make them converge to the continuous uniform distribution. Okay? And it is this weak convergence. So let me state it. Nu n converges to Lebesgue weakly. Weakly. Discrete uniform. Continuous uniform. On 0, 1. This is on 1 over n, 2 over n to 1. Okay, so now with this notion we can talk about convergence in distribution. Convergence in distribution. So let xn be a sequence of random variables and x be another random variable. So we say that xn converges to x in distribution if the corresponding sequence nu n of distributions converge to the distribution nu of x weakly. So we just take nu n as the distribution of xn and nu as the distribution of x. And we say that xn converges to x in distribution if nu n converges to nu weakly. So here's one theorem. So the following are equivalent. Okay, so xn converges to x in distribution. So let fn be the CDF of xn and f the CDF of x. Then we have fn of x converges to f of x at every continuity point of x of f. What is continuity point? You know, cumulative distribution functions can make jumps. So continuity point is a point at which it is continuous. It makes no jump. Okay. So convergence and distribution means convergence of those measures weakly, but this is equivalent to convergence of cumulative distribution functions. Also, it is equivalent to the convergence of Fourier transforms for every R. And there are many other items that you can add to this list. For instance, if they are positive, this is also equivalent to convergence of Laplace transforms, etc., etc. For instance, as an example, so I'm not going to prove this theorem, so we will omit it due to our time limitations. And it is not like a few lines proof. It takes really time. So we're going to omit that proof. But I'd like to discuss with you why this number 3 can be a good way to check convergence and distribution. So let's say you have xn that is Gaussian with mean an and variance bn. And assume that an converges to a, bn converges to b. Some values a and b, okay? So you have a sequence of Gaussian random variables whose means converge to a fixed number, whose variances converge to a fixed number. What we would like to say is that xn converges to some Gaussian random variable with mean a and variance b in distribution. How can we say it? Well, if you look at the Fourier transform of xn, the characteristic function of xn, we have a formula for that, right? I an r minus 1/2 bn r squared. Where does this converge to? Well, these are just exponentials, pluses, minuses, products, etc. So if an converges to a and bn converges to b, this just converges to IAR minus 1/2 BR squared, right? Just usual calculus convergence. These are complex numbers, but you can also separate real complex parts. It's fine. So we just have convergence. And what does that say? Well, this is just the characteristic function of some Gaussian random variable with mean an variance b. So we can conclude that xn converges to a Gaussian AB random variable in distribution. So it is just a one-line check. If you know this theorem, although the definition of convergence in distribution looks maybe difficult and ugly, by convergence of characteristic functions, it is very simple, especially in this Gaussian case. Okay, so here's another result, which is not very difficult to check, but I will skip it as well. Convergence in probability implies convergence in distribution. Okay, convergence, let's say xn goes to x in probability, then xn converges to x in distribution. This is not very difficult. Let me leave it as an exercise. So maybe I should write a comment. So check or use the fact that xn goes to x in distribution if and only if the corresponding distributions converge weakly. And what does that mean? Take any bounded continuous function f, then nu nf converges to nu f. But what is nu nf? It is just the expected value of f of xn. And what is nu f? It is just the expected value of f of x. So just check that. So just check that for every bounded continuous f, the limit of expected value of f of xn is expected value of f of x. And this you need to check by using the fact that xn converges to x in probability, which implies f of xn converges to f of x in probability, because we have a calculus rule for convergence and probability, right? If you have convergence and probability for a sequence, apply a function to everything, then you still have convergence. Apply a continuous function to everything, then you still have convergence and probability. Anyway, so all this effort to finish everything was to actually discuss with you central limit theorem. Okay? It's going to be the finishing point. Central limit theorem. Okay. So here's the theorem. Let xn be a sequence of IID random variables. So it starts the same as the law of large numbers with common finite mean A and variance B, which is also finite. So let's define Sn sum of xi's, okay? So we know that Sn has mean, so note the mean of Sn is n times A, and the variance of Sn is n times B squared, right? Sorry, B, n times B. So here's what the theorem says. So Sn minus its mean divided by its standard deviation converges to a Gaussian 0, 1 standard Gaussian random variable in distribution. In distribution. Let's call it Zn, okay? Let's call it Zn. You can also write it as follows. 1 over square root of n of standardized xi's. So xi minus its mean divided by its standard deviation. Variance, exactly. Thanks. Okay. So what does that mean? So Zn converges to Z in distribution means what? For instance, you can write it as convergence of cumulative distribution functions. So the probability that Zn is less than x converges to the probability that Z is less than x, which is minus infinity to x of the integral of standard Gaussian density for all x. For all x. And this is, again, a bridge to statistics and also simulation, maybe, because this gives you a way to approximate a lot of averages and so on using the Gaussian distribution. For instance, there is Gaussian approximation for binomials, Gaussian approximation for Poissons, etc., etc. Just note the difference. although the assumptions of the two theorems, law of large numbers and central limit theorem, they are the same, you have a different way to take the limit. You have a square root of n, and you also centralize by getting rid of the mean and variance. You make it like a standardized, namely mean 0, variance 1 type of random variable here, which you do not do in the law of large numbers case. You just look at the arithmetic average in law of large numbers. Here, you have a special way to take the limit, okay, by the centralization. Okay, so this is centralization. That's why it's called central limit theorem. Okay. Okay, there is a short but kind of a proof as a sketch. So let's discuss that. All we're going to do is to show that the Fourier transform of Zn goes to the Fourier transform of Z. What is the Fourier transform of Z? It is Gaussian 0, 1, so it is e to negative 1/2 r squared. So this is what we're going to show. This is what we're going to show. So let's look at expected value of ER Zn. What is Zn? It is 1 over square root of sum of those xi minus a over square root of b's. So you have an exponential of sum of random variables. Therefore, you can write it as product of individual characteristic functions. And so this is by independence, right? And since they are even IID, let me say identically distributed, this is just the nth power of one of those things. Let's call it f of r over square root of n, where f is characteristic function of xi minus a over square root of b. So f is characteristic function of f of r is expected value of ei r xi minus a over square root of b. So the original idea of the proof of central limit theorem is to Taylor approximate this around 0. Okay? So f of r can be written as f of 0 plus f prime of 0 times r plus 1/2 f double prime at 0 times r squared plus some term which goes to 0, which is negligible. Let me see how I wrote it, because there are certain ways of writing it. Okay, here's the way I'm going to write it. Just 1 plus h of r. Just 1 plus h of r. So h of r term is the remainder term, and this goes to 0. Okay, where h of r goes to 0 as r goes to 0. So it's close to 0, around 0. It's Taylor approximation or Taylor expansion around 0. Okay, so this is Taylor's theorem. There are some details I don't discuss, but for instance, if you look at f of 0, what is f of 0? Just write 0 here. E to 0 is 1, so this is 1. This is 1. F prime of 0 is in fact 0, so this needs to be checked by using definition of derivative plus maybe dominated convergence theorem, because you need to take derivative of an expectation, which means limit of some expectation, so you might need dominated convergence theorem. So check that f prime 0 is 0. And also, double prime of 0 is 1. So you need to check these two. So if you believe in those results, what do you get? F of r is 1 plus 0 plus 1/2 r squared 1 plus h of r. Right? No, minus 1, sorry, minus 1. Okay. So here's what we get. We were in the middle of a computation, so let's look at that. So expected value of ERZN is equal to f of r over square root of n to power n. So it's power n of what? This expression evaluated at r equals r over square root of n. So 1 minus 1/2 r squared over n, 1 plus h of r squared over n. No, r over square root of n. Did I write it correct? R squared becomes r squared over n, 1 plus h of r over square root of n. Now all we have to do is to let n go to infinity. What is the limit? 1 minus some expression raised to power n. For instance, what is the limit of 1 minus 1 over n to power n? What is this limit? What is this limit? Right? If you have x, this is e to negative x. So this is just e to negative 1 over 2 r squared, because these parts times this converge to 0. So you have n here, you have 1 over n here, they will go away. 1 plus h of r over square root of n. So as n tends to infinity, this goes to 0, and as inside goes to 0, h goes to 0. Okay? So again, this needs some calculus type of check, but it's fine. This is just the characteristic function of standard Gaussian, right? So we're done. Of course, this is a bit too quick, and there are some details that I didn't make precise enough. For instance, the properties of h, and also how to check those, etc. So these are some little exercises for you. But this means we're done with the entire course now. So thank you all for your patience. And I would like to thank Emre Müderrisoğlu for recording us. So thank you very much, Emre Bey, for spending a lot of your time with us. So I hope this is not the end of your probability journey, and you're going to continue learning more. This is just the beginning, so we just covered some basics, you know, just some standard material that is covered in almost all textbooks on probability theory. So the next, so there are possible paths that you can follow. So for instance, you can take a course in stochastic processes with emphasis on Markov chains, Markov processes, Poisson processes, namely processes in discrete and continuous time, but mostly with discrete state spaces. This includes also queuing theory. And you can take another course in more like martingale theory, Brownian motion. You can take another course in stochastic analysis, like Ito calculus, stochastic differential equations, and so on. There are a couple of courses in the university that you can take in your next semester or in your upcoming years. So I hope you enjoyed the course. It was a challenging experience for sure, I know that. And I wish you good luck in your further studies and thesis studies. Okay? So thank you.